Hi there, and welcome back to this channel. I just want to take you guys through something that's very interesting that I've been working on, and I've just find it quite intriguing, hence just want to share it with you guys. I will try my best to be as audible as possible. Let us assume we have a small water filtration system that consists of different cartridges and has a tank as well as a PNID system. And these are some of the ions that I managed to find on DWSIM, such as sodium, sulfide, potassium, magnesium, sulfur, nitrate, and some chloride ion, and literally just salt itself. Look at the constituents of the molarity of our, let us call them impurities that we don't want much of in our water based on the regulations that governs you based on also the city that you live in. So, for example, we have sodium at 0.7 mole per meter cubed, and we have sulfide as high as that as well. Look at the output. Literally everything was filtered through. Even some chloride ion from 0.6, we have 0.0014. I mean, that's fantastic. With that being said, let me take you through the approach. So this is our feed water, and it feeds at these constituents over here. Firstly, we are going to have our filter cartridge. If you're not aware by now, DWSIM does have some form of templates that you can visit. Let me show you, for example. You can actually open one of these templates, and it is a simple membrane template. It has some formulation, and it also uses this particular partial fractions equation. So your permeate flow rate will be basically described by the following components, where this PCI is the permeability for components I, and A, it's your area per unit, L, it's the unit length, the total number of units, the partial pressures of the components in the feed and in the permeate. Now, I literally took this concept. Let me also open for you. It has a script which uses Python calculations. And this is the script that was originally well conducted, drafted on the 6th of December 2011, or could be the 12th of June 2011. We wouldn't really know. But basically, this script was written in 2011, and I found it quite interesting. So I literally copied and pasted most of literally the formulation, just altering this part here. So this is the only part of the formulation that I edited to get as close to as a replica to remove or reject my unwanted components for my water. As you can see from this well-drafted script, this is simple membrane unit operations. So you'll have to alter it now to better suit the type of filtration system you're trying to replicate. And I'll just take you through that just now. Okay, let's go back to my, good, now here we are. So like I said, I pretty much took the concept, flow sheet, I took this concept here and expanded it further to achieve my desired goal. So my water filtration has the following stages, whereby we have a cartridge filter, one with 20 micrometers and one with 5 micrometers. Then we have a GAC, a UF module. We also then have a reverse osmosis, ultraviolet. Then we have a tank that is controlled by a PNID. Just to open a few, remember I said the previous example, while the template itself, if you open this cartridge filter, it's coding. I literally left it as it was, but this time around, we tried to simulate a 20 micron filtration system. And the only part that I edited on this entire particular simulation coding Python coding is this line 66 and 67. I pretty much tried to reach a near zero probability by representing an almost complete rejection. So I pretty much changed the initial amount values to these ones here. And if we go back to compare, let me go back to my flow sheet. If we go back to compare, stream one, let me check it for you guys. Stream one compared to the initial constituents. Remember, these are the pollutants in our water. If we, now you compare that with stream one, you will see that and notice that we have for sodium ion, we have 0.00014. That's great already from 0.7. And for magnesium, we have 0.00125. And ultimately, the water quality is improving. We are now at 99,999.579. And notice how it changes throughout the line. Now let's move to the 5 cartridge filter. Remember here we had the 20, right? If I open the coding for you as well, you will pick up that similarly here, left the coding as it was, didn't change this part here, but nonetheless, those are just notes. Similar to the code that we had, only changed line 66 and 67. Oh, forgot to take you guys through this part here. Remember, the code that was well developed states A represents the area per unit, and then L represents the length, and NU represents the number of units, hence you only have one unit. So yes, you will definitely have to do some research there, you know, to discern and scientifically explain why you're choosing those parameters. But ultimately, the coding for me was well drafted. You can just modify it as per filter that you're handling or dealing with. So similarly for GAC, UF, and all the other modules that you have. So you can see as well here, as we move throughout the line, the water quality starts to improve. We have more of the water and less of those unwanted constituents in our water. For example, the sodium is beginning to disappear. The water now is at 99,999.855. As we move along, now we are at almost, let me see, where are we now? 99,999, like literally, it's the water quality is improving even when we get here as well. Let's see, what does it give us? Yep. After it goes through the reverse osmosis, the water quality is improving, the water quality is increasing, whilst our ions are almost disappearing. Yeah, so we don't have much of the sodium, potassium in there, magnesium is also decreasing, and the water is becoming as pure as possible. I'm a bit skeptical because drinking water should have some type of ions, to keep our body strong. So I'm just gonna say there, water, just to be on the safe side. Before you guys come for me and say, hey, but we do need some form of ions to keep our body strong. Okay, now let's just say water for now. But the guys, I hope you guys get the idea. This is just a concept at the end of the day that I'm sharing with you guys and that I've been working on. I find it so cool. And then we have our tank that is powered and controlled by PNID. Let's open our PNID control system. So pretty much our PNID, we have the manipulated variable being the valve VO2, which is this particular valve here. We do manipulate it as much as we want to retain our water in here. Currently, the residence time is 71 seconds. But yeah, this valve is what is currently being manipulated. And let us see, what is its opening value? I'm curious. It's set at the opening value, well, 31%. Back to our PNID, hence why it's showing you the current opening of the valve, 31%. The property being the opening gap or space of the valve, and the manipulated object is pretty much the valve. The controlled object is our tank, what influences everything. It has these level switch transmitters. This is so cool. I find it so interesting, actually. Takes you back to the industry. It has um, that practicability, the practical part of it brings the simulation to life. And what are we controlling about this particular object? We are controlling its liquid level. The controller is 100% active. The set point here, the water level, it's set at 1.7. That's what we are setting the water at. That's what we want to reach. Um, the set point, pretty much technically. Yeah, so I also have some notes here for you guys in case you want to get some more information. So these parameters here are the tuning points that really influences the impact or how this formula is calculated with our gain, our integral, and also our derivative set at these particular values here. And ultimately, this is just to ensure that if the water level goes past the set point, the PNID controller should pretty much control and adjust this opening of this valve to achieve the ultimate set point that we wish to achieve in this particular tank over here. So yeah, this is a very straightforward simulation example. I hope someone finds it quite fruitful. And I hope it adds value to someone so that, look, you can perhaps design something similar for your school or personal project that you can obviously go and modify, perfect to achieve the ultimate goal that you wish to desire, and the one that you have in mind, of course. So yeah, let's solve it. It does solve pretty much no errors. And for that, I am happy. The water quality at the end, it's phenomenal. You can always obviously manipulate the Python formula for your cartridges, use different type of cartridges, of course, and research on the values that you can input to get the more desirable water quality that you wish to achieve, of course. So yeah, this is quite interesting actually. I enjoyed building it, and yeah, if you want to show alarms, you can just click there and it'll show if it's very low, if it's very high, and you can also have some set values. So what is considered low, what is considered high. For example, high, it's if we are at 3, hence the high went low. But if high is 0.5, it should go red, as you can see, right? Oh, it doesn't read dots, it reads commas, just like Excel, pretty much. But yeah, if you set high at 3, it can look like that as well. Make sure you express the dots, decimals. Got it, got it. Yeah, and can make high 2 infect. That's why it's black. Can make very high 1. You will see it will go red if we set it up as high. Oh no, it's not even 1. Then if I set it on 0, then it should go, got it. But rather, nonetheless, that's high. Low, it's when it's still within 0, it's definitely very low. Need to reach our set point. Yeah, that's very, very low. I think low we can set it at 1 for now. Let's see. Okay, fair enough. But nonetheless, you can play around with it to really achieve. Let's see the percentage. So it's 100% full. Got it. Okay. Yep, you can play around with your simulation, guys, and obviously build. If you really want to be an expert in simulations, just play around with them and discover new information, learn how to use Python within DWSIM, and you really will excel and can work well for you guys. Can even use it for your own businesses beyond just school. So don't forget to always apply what you learn at school also here. I just want to say as well, guys, I also have a PNID system for this software. If you want to see that, you can just watch another video. I will put these all in one group folder, um, playlist, or I will just link it actually to this video. Yeah, so at the end of this video, the drawing in terms of PNID, how to draw a PNID for this software will be linked to this video as well. Okay, now stay tuned and thanks for watching. Cheers, bye.